So Cesare Stefano asked me to have an Ignite talk, so I had to think a little bit what exactly I had to ignite. But I decided to just give, for the Ignite talk, a brief overview of what I think are the hot topics from the methodology point of view in fMRI and why I think that's the case. So obviously, I don't need to make a case anymore that MRI is a great machine. And although, of course, the purpose now is not to go into the mathematics and the amount physics, but honestly, if you think about the basic mechanism of how the MR signal is acquired, from the MR physics and actually the quantum physics that are involved, and you realize that it actually works in practice in living tissue, I'm still surprised by this. It's really amazing. And so you can use it, of course, to do this beautiful structural kind of imaging. You've seen in Matteo's talk that you can do diffusion-weighted imaging to even reveal within the tissue that you can already recognize here the structure within that is invisible in this type of structural images. But of course, and I think there you didn't hear a lot about yet, you can also use MRI in a functional way, which means you can track brain activity by a proxy for brain activity, which in the real talk you will go deeper into. And so this is just the same principle. You require volumes sequentially of the whole brain. Of course, you want to do that very fast because you want to track brain activity. So you basically spend 1 to 2 seconds to acquire a whole volume. And what you see here, it's moving. It's a movie. It's a sagittal slice of a functional scan. And so you see that you need to give up a lot on resolution, on tissue contrast, which is not very great. And that's not the problem, because what is really interesting for us now is how this signal will have tiny changes over time. And those can be related to brain activity. Now, just for the history a little bit, since the beginning of MRI in the early 90s, this was the basic paradigm to use it for brain mapping. And so basically you had some stimulus or task to which the subject in the scanner attended. So let's say you have this very salient flashy checkerboard, which obviously will activate the visual cortex. And so you acquire these snapshots of the brain, and once you have, well, the stimulus will evoke activity, and once you have acquired all the data, you will go into offline processing, which involves a lot of tricks and statistics to give you a map of where in the brain do you have evidence that something is happening in terms of brain activity related to the stimulus or task. And so this has been done for more than 20 years, and it's still a very important paradigm that can be used. But of course, we started to realize, also because the signal quality got a lot better since the early 90s, that the brain is not only processing those stupid stimuli or tasks. So it's doing many other things it actually has to do. And one of the challenges, to come to the first one, is to develop tools that would be able to look at ongoing brain activity, which can be completely unrelated to a task or a stimulus. So it can be resting state fMRI, but it could also be just background activity during a task. And to disentangle that in terms of, here this is just one methodology, but in terms of functional networks that come online and go offline, if I call it like that. And ideally, that you would be able to interpret and relate to behavior, such that you can have an idea what type of cognitive activity the subject is engaging into while being in the scanner at any moment in time. So this is one of the challenges. There are techniques that are trying to get there, but it is challenging. And I think one of the keywords there is dynamic analysis. So I guess many of you have heard of dynamic functional connectivity, which is basically taking into account the time resolved and the time varying nature of brain activity instead of computing just summary measures over a whole scanning session. And that is the first step to, of course, appreciate the moment-to-moment variation in brain activity. But it's just extracting more sophisticated measures The really complicated step is the next one, which I will call coming up with computational dynamic models, which will actually really try to explain what you're observing in these more sophisticated measures of dynamic functional connectivity. So this could be models such as hidden Markov models and others that basically summarize into an interaction diagram, as you can see here, how, for instance, when the attention networks come online, how does it influence the default mode network? Or how does it influence the sensory networks in general, etc. So all these more system levels, complicated interactions need to be summarized and interpreted. And of course, once you have models like this, then you could relate them to neuropsychology or to clinical scores, etc., which in turn might suggest certain mechanisms, which in turn could suggest a new experiment, and so on and so on. So I think we will slowly engage the next years into this type of what I will call more computational systems level neuroscience. Okay. So this boils down to coming up with new measures or new models for integration in the brain. One of the associated challenges will be that with this functional analysis, we need to take into account, of course, the structural background. All the beautiful talk by Matteo showed you that you can extract today the scaffold of the brain. And so how do we take this into account in our functional analysis will be also an ingredient to appreciate, and that's actually the purpose of the Brainhack literature. And relate this to function, dysfunction, and also behavior, of course. So you can put this under the denominator of understanding organizational principles, network organization, dynamics, interactions, all keywords that are very much related to it. And one of the main reasons we can start doing it today is that the data is there. There are many huge brain acquisition, brain imaging initiatives. The Human Connectome project, of course, is one of the leading ones. But many others are ongoing and will deliver data in the very next month. So, and that's, of course, what you need to do this type of systems level neuroscience. You need a lot of data. Usually you cannot do that with a low number of subjects. This said, I think the greatest benefit is probably if you can combine big data from, let's say, standard repositories like the HEP to extract things for which you need big data, but then apply them in some way or another to your specialized local data set with a very particular paradigm which makes a lot of sense for your research question, or specific cohort of patients which are difficult to acquire and we don't have public data. And so I think if you can make a mix of both, where somehow things you cannot easily extract from a low number of subjects, you get it from the big data sets, and then extrapolate this into your specific data. I think there you can really find nice niche applications. And then the final frontier I like to mention as the end of this Ignite talk is the close the loop. Right? Can we use fMRI, the real-time processing of the fMRI, and extract what I call a neurofeedback signal? And the purpose of it, let me show it to you. So we will still do fMRI, but now we will all do all the processing, like the realignment, the correction for artifacts and so on. We will do it in real time, which means within a second, basically, you need to have processed that incoming brain volume. And you will use that to extract a measure of some activity, some type of activity somewhere in the brain, which is relevant for you. And you can then present this to the subject in a visual way, which could be a thermometer view, like you see here, but there could be more attractive ways of visualization. And so, because you make this now visually available to the subject in real time, if this reflects a certain type of brain state, the subject can now consciously access this brain state, which is something you cannot usually. Okay, we don't feel our own brain activity. Right? We don't have sensors for that. And so then by the principle of biofeedback, and operant conditioning basically as a psychological process. If you ask a subject to learn to regulate the signal, for instance, upregulate it, and if he feels rewarded by succeeding in doing so, and since you close the loop, he has a certain sense of agency after a while, and he can actually learn to regulate many types of neurofeedback signals in this way. So it's really about enabling a conscious access to his own brain activity or her, and then as a consequence of that, being able to regulate the associated brain activity that you visualize in the neurofeedback system. And with that, I basically finish my Ignite phase of the talk. If you have any questions, happy to answer.
Is there any question?
Yeah, we're talking about system neuroscience. And when we talk about system neuroscience, we usually talk about big regions. But in fact, the brain doesn't work with the entire dorsal prefrontal cortex. It doesn't work with the whole angular gyrus. It's like you have layer-specific activity, and for that, and different levels of myelination and different properties across the layers of the tissue. So, my opinion is that how do you see that these two walls are going to merge together? Because people is going to 0.5 isotropic resolution, 0.5 millimeters isotropic resolution. But then when we talk about system neuroscience, we are talking about like 1,000 millimeters cubic.
Yeah, so I mean, very good. Like yeah. I think systems neuroscience you shouldn't necessarily associate with an atlas. Of course, today it's the most common way to do it, right? To do whole brain analysis and so on. Now, okay, obviously you can go to better atlases. If you go, instead of AEL, you go to Glaser Atlas, you already make a good jump forward, and the atlas is informed by cytoarchitectural features and so on. So then you have already 360 regions, and probably we will have better atlases in the next years. Now, this said, I think, depending on the question and the method you're deploying, you can also go with voxel-wise analysis, even in this whole brain exploratory way. So I will show you in the Brainhack talk. The first part will be based on the Glaser Atlas, and then there will be a highlight where we actually use voxel level graphs. Okay. So it's a matter of method development and of course computational resources at some point and storage, but I think it's within reach already today.
I think this is a challenge, how to merge the two worlds, the really physics and methods development in terms of the acquisition, how to improve the data, the analysis for layer-specific MRI, because we know
that's
that
frontier.
It works in different thalamic nuclei, different layers of the cortex, in V1, in V2, in V3, and then how to merge them with those models of connections between different layers. That's the next challenge on how to.
Yeah, if you go to layered
models,
models,
combine that and how to constrain those models using a structure, using quantitative MRI or diffusion MRI.
Yeah, these are open questions, absolutely. But it's only today we are getting that data available, so it will take a while to digest it and to integrate it in new methods. Matteo.
So very nice announcements. But since you already mentioned the big data study, right, which are very useful, very important stuff. At the same time, we know that if I scan your brain on the Prisma here, and I scan your brain on the Prisma in Geneva, I'm probably going to get different numbers, right? Different different
to some degree.
So we do have a big problem in data harmonization, right? To be able to
I think it depends on the question. So, as I will show you in the Brainhack talk, there we are constructing a high-quality structural connectome, which is supposed to be a generic one. So it will be averaged over 110 HEP subjects. So then it becomes quite stable, obviously, right? If you now want to look into the reproducibility within subjects and then look at the variance between subjects, it is a question on itself. I don't think we have a definite answer already today. But sure, yeah. But thanks to the big data, we will be able to answer to it. Since in the HEP we have a test-retest, we can do already very nice things in terms of reproducibility of resting state fMRI, task fMRI.